Hey everyone. Because our time in class today was limited and we didn't quite get through as much as I wanted to get through in class, I wanted to do another example problem for you so at least you have some more reference. You can go back and take a look at some things that we did. This problem actually is from page 152 of your book. There's a section up at the top. It's the second part of the practice problems section. So the practice problem section actually starts on the previous page on page 151, but this is actually at the top of page 152. It goes through both of the things that we did in class this morning, finding the resultant vector of two non-perpendicular vectors, and then also going through the equilibrium idea. So anyway, let's run through this. So number 3 says two ropes pull on a ring. One exerts a 62 Newton force at 30 degrees, and the other exerts a 62 Newton force at 60 degrees. We'll assume those are from the x-axis, assuming that the positive x-axis on an xy coordinate is going to be 0 degrees. I'll draw them in just a second. So two parts here. What is the net force on the ring? And what are the magnitude and direction of the force that would cause the ring to be in equilibrium? So we'll start off with this picture. And here's my ring. There it is. And it says that we have two forces, a 62 Newton force at 30 degrees and another 62 Newton force at 60 degrees. So I'm going to put myself in a little x-axis, a little y-axis. I'll adjust my ring so that it's approximately in the middle. And I'll draw my two forces. So it says a 62 Newton force at 30 degrees. So I'll draw that something like that. We'll label this as 30 degrees, this as 62 newtons. And then it says there is another 62 Newton force at 60 degrees. So I'll pull this here like that. We'll label this as 62 newtons as well, and then we'll label this whole part here as 60 degrees. Part A says, what is the net force on the ring? That's a fancy way of saying what is the resultant force on the ring, right? The net force being the sum of all forces, the resultant vector being the sum of all vectors. So all that's asking you for is the net force or the resultant vector. In class today, we went through how to find the resultant vector of two non-perpendicular vectors. So first thing we have to do, these vectors are not oriented the right way to find the resultant vector. If I'm going to take my blue one and I'm going to move it to here. Did I have to move the blue one? No, didn't have to move the blue one. But I had to move one of them so they're lined up tip to tail. I'm going to take my 62 this way, and then I'm still going to take this 60 degrees and put it here. Even though it's not in relation to the x-axis anymore, that angle is still 62. This is going to be my resultant vector. The vector that starts at the beginning of the first and ends at the end of the last one. So we said the first thing we do here is we have to break up each of our individual vectors into their x and y components. For the red vector, it's going to look something like this, right? It's got an x component here, it's got a y component here. Then for the blue vector, it has an x component here, it has a y component here. In both of those triangles, we know the hypotenuse, that being 62 newtons, and then we also know an angle in there. So we can use our sine, cosine, tangent functions to find the individual sides. Do that now. Because we're dealing with a 30-degree angle and a 60-degree angle, the sine and cosine are flipped, and that works out well for us. But anyway, so we said once we've broken everything up into their components, in essence, what we've done is we've taken this solid blue one out, replaced it with those two components, and then taken that solid red one out and replaced it with those components. Next step, add all the x's, add all the y's, and we'll end up with one big right triangle. So if we rearrange a couple of things, I'm going to bring this blue one down here and take the 31 with it. Bring this red one over here, take the 31 with it. If you remember your geometry stuff, we're going to be in business here. But the big idea being that if these two are both along the x-axis and they both point in the same direction, that means we can add them together to create one big side. If these two are both on the y-axis, both point in the same direction, we can add them together. And we end up with, just like we did in class, one big right triangle where the purple vector, being the resultant vector, has to be the hypotenuse. So go ahead and find out what the value of that purple vector is, the magnitude or the force that's required, or the force that's the net force, and then the angle as well. So when you run that all through, you should end up with 119.7, or 0.8, I guess. Sig dig-wise, we'd probably go to 120. And that's going to be in newtons because it's a resultant force. And then here, with the two sides being the same, that's going to be a 45 degree. So 120 newtons at 45 degrees from the x-axis. That would work in this case because we don't really have directions to work with, so that probably won't do well for us there. Okay? Now, for part B, it says, what are the magnitude and the direction of the force that would cause the ring to be in equilibrium? Okay. That being said, let me go here. I'm going to clone this page. No, that's not what I wanted. Undo. Okay. And I'm going to get rid of a couple of things. Namely, this. And all this junk down here. So, we talked about in class that cause the ring to be in equilibrium. We talked about in class that the definition of equilibrium, or the concept of equilibrium, doesn't change. It's still no net force, or net force equal to 0. But we talked about that in class, that when we go to 2 dimensions, in order for something to be in equilibrium, it has to have no net force on the x-axis, but also no net force on the y-axis. If we look at the resultant vector that we just found out for those two forces, in order to make equilibrium, we're going to have to do this. We're going to have a force on the x-axis that is exactly opposite of these two put together. And on the y-axis, we're going to have a force that is exactly opposite of these two put together. So now we know what we need to create equilibrium. We need a force of 84.7 on the x-axis, but pointing the opposite direction. And then we need a force of 84.7 on the y-axis, also pointing in the opposite direction. The force that produces equilibrium is going to be the resultant of those two individual forces. But these are both x-axis, y-axis, they're perpendicular. So we just take one, bring it here, I'll bring the 84.7 down with it, and we know how to handle this. It's just finding the resultant vector of two perpendicular vectors. And it goes something like that. Any guess how big that force is going to have to be? If you're astute, you probably do. This, take my number with me as well, this, which was the resultant force, or the net force of those two original forces, has to be the equilibrium. But if we look at the value and the direction, it's going to be 45 degrees again, but we probably adjust that to being 120 newtons at 45 degrees from the negative x-axis, or we could say, the way I have it labeled here, technically this would be 45 degrees from the negative x-axis. This would be 45 degrees, 120 newtons at 45 degrees from the negative y-axis. And that would give us this angle right here. So, two things. One, we first found the resultant vector of two non-perpendicular vectors, right? Split them up into components, add the x's and y's, find the hypotenuse of the right triangle that's created. Then, to produce equilibrium, we have to balance out those forces that we didn't balance out, or that weren't balanced out to begin with, and that's just going to be a component on the x-axis, same value, opposite direction, component on the y-axis, same value, opposite direction, find the hypotenuse.